Hello everyone, welcome to this lecture 7 in the module Dielectric Properties of Insulator. And in this lecture, my plan is to introduce the concept of microscopic and macroscopic field. So to set the background, if you recall that so far we have discussed in the previous, I believe in 3 lectures, 3 different types of polarization that mainly contribute to the material, right? And the first one was the electronic or the atomic polarization. Second one was the ionic polarization or the displacement polarization. And the third one was the oriental polarization due to the presence of permanent electric dipole moments in some materials, right? And we have discussed in detail these 3 different types of polarization in the previous lectures. But here I want to summarize. The fact is that the expression that we obtained for atomic polarization, the electric dipole moment for a single atom, right, the P atomic was alpha atomic, which is the polarizability of the atomic polarization, and times the atomic field, right, the electric field felt by the individual atoms, right? So that's really a microscopic field. Similarly, when we discuss the ionic polarization, which really occurs because of the displaced ions from the equilibrium position under the influence of some electric field, right? So we have discussed this in the previous lecture, but the key message that I want to bring in this lecture is that similarly, when we found the expression for the contribution of a single ion in a, let's say that's our unit cell, consists of a positive and a negative ion, and then we found the expression that the contribution for an ionic dipole moment is nothing but alpha ionic, which is the polarizability of ionic polarization in the material. And then the electric field is not the external electric field, right, which is macroscopic, rather the field that experienced by these ions, right? And we assume that because the distance is so small between these 2 ions, we assume that both of these ions really feel the same electric field, which is E ionic, right? And then we talk about this oriental polarization, where we have some dipole, permanent dipole moment, and then under the influence of electric field, they align, some of them align, but not all of them because of the thermal agitation. But the key point is that here the similar expression is valid, right? So the oriental polarization is nothing but the alpha OPD, which is the polarization of the oriental polarization, and then the electric field felt by the dipole moment. So you can see in these 3 cases, here we are talking about the electric field on an atom, here we are talking about the electric field on ion, and here we are talking about the electric field on the permanent dipole moment. So dipole, right? And the idea is you can see the sizes of these elements, right, dipole, ions, and atoms are really microscopic, right? And if one calculates the total polarization due to these 3 contributions, you need to add them up, right? The atomic, the ionic, and the oriental polarization. And then you set up the expression for in terms of this electric field and the polarizability. I'm just putting the expression here. And then let me just make one assumption, which is quite accurate for many discussion, is that since the sizes of this atom or ions or dipoles is of the same order, then we can assume that the electric field felt by these elements, like either atom or ions or dipole, whatever it is some local, right? So this notation is mean that the electric field, which is very local at some point R, and R is where the atom or ions and dipoles are sitting. And so I am simplifying that all these electric fields are denoted by a single local electric field. And also when we are calculating this polarization in the material, the total polarization, this is also a microscopic, right? Because on the right hand side you can see we have these fields which are really local fields, so the polarization must be local too. So that's why let's use the total polarization as some local polarization, and the subscript log is denoting the fact that this is a local polarization in the material, right? And let me simplify some of the notation here. That let's assume that P alpha atomic is nothing but alpha A, and alpha ionic polarization is also known by the displacement polarization, because they really due to the displacement of the ions in the unit cell from the equilibrium position. That's why let's denote the alpha ionic is alpha D, and then the oriental polarization, let's just make it a bit simple and let's assume this is alpha PD. So from this expression, all of these electric fields are some E log, so you can take the cofactor out and you can simplify this atomic, ionic and oriental polarization by these notations, right? So we are assuming there are three types of polarization are acting in the material, whatever material we are considering, right? So it's a kind of, we are summing over these three polarizability. One is the atomic, then the displacement, and then the permanent dipole, right? So it's kind of, we are summing over these three alpha i's. I is equal to 1 is atomic, I is equal to 2 is the displacement, I is equal to 3 is like the permanent dipole, right? And let's say this sum, total polarizability, is sum alpha, right? Sum alpha, to make the notation a bit simple. Then we can see we have arrived at expression is that the local polarization of the electric dipole moment at some point R is alpha times the location of the electric field, the local electric field at that point R, times the total polarizability of that material. So these are really very consistent expression for the material, but the crucial point is that although we know how much electric field we are applying this material externally, right, that's easy, but we really don't know what is this local electric field. So that's why in the study of the dielectric material, it is also important to understand the distinction between this local electric field and the external applied electric field, right? They are not same, and we want to make this distinction, right? And for that, let's try to understand. Let's say we have a piece of one-dimensional solid, and you know the solids, there are many atoms, right, periodically arranged in a crystal lattice, let's say, and let's say that atomic distances, which is very small, right? So like the two nucleus are like 1 or 2 angstrom apart. So these are really very small distances, right, of the order of some angstroms. And you can see that, let's say we are plotting the charge density of these atoms, right? And you can see when we have some ions, right, these are positively charged nucleus of the material, so the charge has a peak. But in between the ions there is no charge, so the charge kind of diminishes to a small value, right? So you can see the fluctuation is in the order of angstrom range. So this microscopic, let me be specific, the microscopic charge density inside the material is oscillating with a period of angstrom, right? So this is a really, really local oscillation and very rapid oscillation, because the charges are producing these individual peaks in the oscillation. But that's a rapid oscillation in the microscopic charge density, right? But you can see the average of this oscillation is a smooth line like this, right? And you can see is that, let's say over some distance, if somebody asks you what is this black thick curve is doing in this small angstrom range, you would say, okay, it's almost same, right? It's almost the same. So although the microscopic field is fluctuating in a rapid scale, but the average field is not really varying in the angstrom range, right? So in that case, this is almost a constant. So to see this black curve is deviating, right, we need to take like certain lattice point. Let's say how many we have taken here? 1, 2, 3, 4, 5, 6, 7. So we are saying that if you look some distance, let's say R0, right, some distance, which is of the order of 7 lattice point, right? So this is 7 lattice point. If you look in this range, now you can see, okay, well now this is the flat line, but now you can see the slow variation, right? So you need to go up to certain distance, some certain number of atomic distances to see the average of the macroscopic field varying, right? But if somebody asks you what about in R0 the macroscopic doing, this is doing like a rapid fluctuation, right? So that's the difference. This thick line, you can think of this is a macroscopic, right? Macro means large, so macroscopic, and this rapid oscillating curve is the microscopic charge distribution, right? And this is always the case that if you consider these local fields, right, this micro is really what we always term in this context of dielectric material is a local field. So the local fields are really fluctuating. And also you can see that for macroscopic charge densities, right, the spatial variation is only visible over some distance R0 or greater, right? Because if you are in too small distances, then this field is this fluctuation is almost a constant. So this is the difference between the microscopic and the macroscopic field. And recall, you have written the Maxwell's equations in your different courses many times, right? Let's say the first one was the divergence of the electric field is nothing but the total charge density divided by the epsilon, right? We have discussed this equation in many times in this course, but we never asked the question, what sort of charge density and what sort of electric field really we are talking about. So far, all the electric field or all the charge density, those are macroscopic. So from this lecture, you can appreciate the fact that when nobody is really distinguishing this microscopic and macroscopic thing, then every electric field and every charge density in the equation was in the macroscopic world, right? So to be more explicit, one really should explicitly say that this is a macroscopic charge density, this is a macroscopic electric field, but we often don't do it because this is kind of implied that if we don't mention, then the obvious thing is it's a macroscopic quantity. So if somebody asks you, then what should be the corresponding Maxwell equation for the microscopic field, then you have to say, okay, now we need to find out the divergence of electric field is always the case, but not the macroscopic, rather the microscopic electric field. And on the right hand side, the charge density must be microscopic, right? Divided by the dielectric of the permittivity of the free space. That's the difference between macroscopic and microscopic fields. Like the discussion can be extended to magnetic fields and every field that we have encountered in our discussion of electromagnetism. But for this lecture, the two things that are important is the charge density and the electric field, because we are talking about electric dipole moments inside the solid. So the quantity of relevance here is really the electric field and the charge density. That's why we are kind of limiting our discussion in these two quantities. Now the obvious question is that, okay, we always write down this macroscopic Maxwell's equation, but we know there's another Maxwell's equation, the same, where the quantities are at microscopic level. So the question to ask is that once you are given some microscopic electric field, how do you calculate the macroscopic quantity, right? So the question is, how do we go from this microscopic quantities to the macroscopic quantity, right? That's a very important question to ask. Now, let's say the answer is that we need to perform some averaging, right? That's always the case. We will perform some averaging. And let's say, I will give some example that when you were calculate some expectation value or some average in your statistics courses, right? Let's say the mean of something, some variable x. What did you do? You take the variable itself, you multiply it with some density function, and then you integrate, right? So that's the definition of some averaging. A similar concept will be interpreted here, but for that we need to understand the density of the weight function. So if you look at this integration, it is as though we are integrating over x, right? So different points on x, and we are multiplying the value of x at that point times the density of some function at that point, right? So it's kind of a weighting function. You are multiplying a certain weight with your variable, right? So the density function is certain weighting function. That's another way of visualizing what is this probability density function is doing, right? It's weighting the values of the variable. So similarly, let's say we have a piece of solid, and although we know the solids are two-dimensional, solid is always three-dimensional, but here to explain the thing, I'm taking a two-dimensional lattice, right? So in two dimension, what I'm drawing here is a circle. So you can imagine in three dimension, this will be just a sphere. But the important point to remember is that, let's say these are the lattice points in the solid, right? So we have some atoms in individual places of this is really in the microscopic range, and the distance between these two lattice points is some angstrom, right? It's a very small distances. Now, let's say somebody is asking you that what is the electric field at this point. So that's your local electric field at some point P. So let me write down the quantity first. We want to know what is the, let's say, electric field at some point P, right? But the local field, right? So we know that we have some value of this local field. So the question is, then what will be the electric field at this point, macroscopic field in this point P, right? So we need to understand how we do this averaging, right? So for that, we need to invent a function or weighting function, right? Let's say we are saying that we have some weighting function for this averaging to take place, but the weighting function is Fr. So that's the position in the real space. So every point in this space has some coordinates r, right, in two dimensions. So that's not the problem. And the function should satisfy, as many of these characteristics of function is similar to the density function. You recall the density function is always positive, right? So similarly, the Fr, the weighting function for the average, has to be non-negative. So every time it will be a positive valued function, and then the range of the function. So this function is only non-zero if you are within this R0, some distance R0. Maybe this is a radius of 1, 2, 3, 4, 5, 6, 7 lattice point, right? So I am talking about some circle which is of radius 7 lattice point from the point P, right? So if the function is such that if you go beyond this circle, this is 0. But if you are within this circle, the function has some non-zero value, and we don't know what's the value of this function. That's another characteristics. And number 3 is that, like the density function, you remember the density function usually are normalized. So what I'm saying that if you integrate the function over the space, right, that will give you 1. So that's the normalized condition of the function. And also the symmetry of the function is such that it's an even symmetry, it's an even function. It means if you look at any point minus r, it should be the same as the plus r, right? So let's say we are considering at some value of the function at this point, this should be equal to exactly opposite minus r at about this point, right? So these are the characteristics of this function. Let's say we have such function, and then with this function we want to perform the averaging, right? And how do you perform the average? You can think something like that. So the quantity that you want to average over times the density, and then you need to integrate over the variable, right? So here the problem, you can see, I am saying that whatever inside this circle, whatever the points we have, all the points will contribute to this point. But if you go outside, the contribution will be 0, because the function really vanishes outside this circle, right? So that's how the averaging process. So to find out the field at that point, I will take the contribution of every point inside this circle, or in 3D some sphere, okay? And then let me write down the electric field. The electric field at the point P. So let's say some RP, or maybe some R. To be more general, let's say we have some origin here, and we are saying that this is the coordinate position of that point, and we want to understand what is the electric field at that point, right? This is nothing but the quantity that we know, that's the microscopic field, right? So let's say, let me be specific and explicit. So E micro, right? That's the field. So those fields are acting on the local points, right? For every of these lattice points. Now we will shift this field. So by changing the argument from R to R minus R dash, it means we can kind of move from point to point by changing the R dash, right? So that's the quantity that we want to average over. So that's like X. And then we need the distribution of the weighting function. So what is the weighting function for us? That's like the FR. But we will pick the point at FR dash, right? The value of the function at that point, because we will perform the integration over dr dash, right? So now we can kind of make a correspondence how we perform the average. Here, to find the electric field at some point R, what we do, we ask ourselves what is the local field at every of these points, right? So let's say R dash is at this point, and then R dash can be at that point, and then the R dash could be at that point. So we ask what are the microscopic field of individual points, and then when I pick, let's say at this point, I know what is the micro, which is denoted by R minus R dash, and with that I multiply the value of the function at that R dash point, right? We know the function and is non-zero of some value, and then we integrate over some volume element centered at the R dash, which is this dr dash, right? That's the volume element of 3 dimension, or whatever 2 dimensions is the area element. So this is quite general. You can extend the volume to 2 or 3 dimensions, doesn't matter, right? So that's how you perform the averaging. The microscopic electric field is averaged over with the weighting function FR dash, right? This is a very important equation to remember. And the question to ask is now, okay, what is the advantage of doing the averaging like in this form, right? Let me mention the advantage of doing the average in this fashion. So let's say we consider this point that we are trying to evaluate the total macroscopic field, which is ER, but we know what is the individual electric field at these points, right? These points. So let's say we are talking about on this point, and this some points within the circle, and this is denoted by E micro R. Let's say within this R naught, the microscopic field is not really varying that much, right? So what I mean by that is that the E micro R dash, this is not really varying that much. Let's say within this circle, every point has the same electric field, right? So we have some E micro for the point R. So it is kind of independent of R dash. So whichever point you choose, it doesn't matter. It's shift invariant. It's kind of everywhere the same. So then the microscopic field is just R. So can you see that when this thing becomes independent of R dash, and you're performing the integration and the weighting function is all function of R dash, so this can be brought out from the integration, outside the integration, right? And then we have left over the integration of the weight function. But by properties of this weighting function, you know, when you integrate over this function, this is nothing but 1, right? So what that means is that the macroscopic field at any point is equal to the local field. When is the case? Because I don't see any variation over every point around this R naught. So whatever the field is here, the same should be here. That should be your E local field, right? So the way you perform the average, it makes sense and then it will give you the exact local field equal to this macroscopic field, because there is no significant variation within this sphere, right? I hope I am able to make this point. This is really crucial, and this will become handy in the future lectures where we use the Lorentz technique to find out the strength of this local electric field. And I think with this, that's about it for this lecture, and thanks for listening.